This conference will
Okay,
now be
so
recorded.
let us start the session. In the previous class, we were discussing things with respect to the I2C communication protocol. We have understood how the two chips of the same board are going to communicate with each other with the help of I2C communication protocol. So that was an example for a intra-board communication protocol where you want to establish communication between two chips of the same board. So by now we are done with four communication protocols. I mean three communication protocols. First one was UART, second one was SPI, third one was I2C, and this the very last communication protocol we are left with to be discussing about is nothing but the CAN communication protocol. So I'm hoping you people have no doubts regarding the previous topics we have discussed so far. So today we are going to start with the next and the last communication protocol, which is nothing but CAN. And CAN stands for Controller Area Network. Now, do you remember which company got this CAN introduced? Do you remember the company who introduced this? Yes. So it's Robert Bosch. So this CAN communication protocol was one communication protocol which was introduced by the Robert Bosch company. They actually had a need of the network, which was in fact a very highly reliable and a very simple protocol. So they worked really hard and they introduced this communication protocol by the name CAN. Actually, if you go with the history, or I would say if you go with Google and try finding out this, the reason or the story behind the CAN communication protocol, they actually speak a lot about a car. Okay, so the very commonly taken example for uh, taking the history of CAN communication protocol is generally the car. So what happens in a car is you will have multiple things to be controlled in case of a car. Okay, so it's like we have a steering, we have a window, we have brakes. So like this, we have got several things like that of a human body. So car also has certain functionalities to be taken care of. So in our body, as we have so many nerves going around the organs connected with each other, so when it comes to the car also or any hardware you take, so things are connected to one another with the help of a wire. Okay. So when they actually started, they wanted to design an automatic device. Okay. So like as the technology kept improvising, so even today, so technology has been going very improvised. So every day there is one or the new thing coming up in the market. So as the technology improvised, they wanted to make things automated. So their focus was to design a automatic device. Okay, so they wanted an automatic device to be designed. Now the problem is there was a network which can connect each other together. Okay, and in fact the network what they used was very complex. Okay, and due to that reasons these components must have to talk with each other. So due to some of the reasons, as you already know, the chips in the same board or chips in two different boards may have to communicate with each other for the smooth functionality of the automatic device you're trying to implement. Okay, now there was already a network, and as I said, it was very complex with too many wires. Okay, the number of wires which were used to connect these components were really huge. Now, if anything went wrong, so we don't know where exactly the problem is. They might have to rectify each and everything. They might have to examine each and everything to know what exactly is the problem. So what they wanted was they wanted. I'm not audible, Vinita. Am I not audible? Okay. So they worked really hard. They wanted the things to happen very smoothly. They wanted the communication to happen very smoothly. They wanted to reduce the number of hardware lines that have been used. and they tried introducing a communication protocol called CAN. Okay, so mostly, like at the very initial stage, CAN was introduced just to make an automatic device, to make things automated. But now the CAN is being used in so many other fields. It has been used in avionic fields. It has been used in commercial applications. They use it in lips. They use it in many other fields. And what do you think CAN is? So, is it an intra-board communication protocol or an inter-board communication protocol? It's a inter-board communication protocol. So both UART and CAN are inter-board communication protocols. SPI and I2C are intra-board communication protocols. That means communication should happen between two chips of same board or different board. So it has to be two different boards. Yes. So communication between two chips should happen on two different boards. Now let us start with the introduction to the CAN. So here in this CAN protocol, we have five major things to be discussing about. First is introduction to the CAN. Second one is the basic concepts of CAN. Third one is how the message gets transferred with the help of CAN communication protocol, how errors are handled, and how fault confinements happen. So how faults are handled in case of CAN communication protocol, we will discuss. So moving ahead, starting with the introduction to the CAN, the very first feature is it's an asynchronous communication protocol. Now, what do you mean by asynchronous communication protocol? So what is absent? There is no clock, right? So because there is no clock, what do you need? Yes, there is a triggering mechanism required for the communication to get established. Then apart from that, this is a half duplex communication protocol. What do you mean by half duplex? Yes, so no master, no host. Okay, so yes, two-way communication, but only one can communicate at the same time. That is half duplexity. So in order to achieve half duplexity, what should be the direction of the data line? So yes, it has to be a bidirectional data line. Okay, so it has to be a bidirectional data line. Now, because it's an asynchronous protocol, can I consider the devices as master and slave here? No. Okay. Uh, uh, Sorry, one second. Abdul is asking UART and CAN both are asynchronous. So can we say all interboard are asynchronous? No, Abdul. So that is not the right statement to make. So there might have been a communication protocol which is synchronous even when if you take UART itself, there is USART also. Okay, we saw it in our own microcontroller. So in USART, it was a synchronous, asynchronous communication protocol. So synchronous can be there when you are having a interboard protocol also. Okay. So yes, sir. Because it's an asynchronous, I cannot consider the devices in the network as master and slave. But it's a multi-master, multi-slave communication protocol. So as there is no clock being involved, as I cannot call the devices as master and slave, so in this communication protocol, we generally call the devices as, we call it as nodes. So in the UART protocol, we were referring it as host and the device, but here we call it as nodes. Okay, every device in the network, we call it as nodes. So now this is the basic feature of CAN protocol. It's an asynchronous half duplex protocol with multi-master, multi-slave. I would say multiple nodes in a given network. Now coming to the basic concepts, we have to start with the example, some versions. So what happens when there is an absence of node addressing and all. So we will discuss each one of them one after the other. Okay. So now let us start with the example. You can see here, every device in the network are called as nodes. So first one is node 1, next you have node 2. So that way you have until node n. Okay. So every device in the network are referred as nodes, and this is a slide which is telling you things with respect to the examples of the devices in the network. Now you may have n number of devices in the network. Okay. And every node here in the network, as you can observe, should have three different things. So one is the controller, the second one is CAN controller, and third one is CAN transceiver. Okay, so every device is called as node, and you can have n number of nodes in this network. And the typical components of these nodes are, there are three things to be available on the nodes: controller, CAN controller, and CAN transceiver. So every node should have these three components for sure to be qualifying as a node in the CAN communication protocol. Now you have to understand what happens in each of the things. So first, if you take the CAN transceiver, okay, so this is the one which actually works with analog and digital values. Okay, so it is one side analog, the other side digital. Okay, so there is a CAN transceiver. So this is analog side. One side of the transceiver is analog. The other side of the transceiver is digital. Okay, so any CAN transceiver you take, one side it's an analog working, the other side it's a digital working. Now if you see, there can be some nodes which will have controller and CAN controller built in. Okay, so something like this. You may have controller and CAN controller built in. So you may just have to add CAN transceiver separately to make it a node. Okay, so that is possible. And in some of the cases, controller has to be brought separately, CAN controller has to be brought separately, CAN transceiver has to be brought separately, and all of them should be interconnected to make a node. Okay. So one possibility is all three you are bringing it separately. Another possibility is controller and CAN controllers are built in. Only CAN transceiver should be added separately to make it a node. Now, so far we don't have any such nodes which have all of these three things built in. But going ahead, as the technology is improvising, as the industry is growing, so you may come across a node which will have controller, CAN controller, and CAN transceiver already available inside it. But as I'm saying, as of now, we don't have such device which has all the three present in a single chip. Okay, are present on a single board. We don't have that option as of now, but going ahead, you may come across a device which supports CAN controller, which supports CAN transceiver, and also has its own controller. So that is possible. But remember only one thing: every node here should have a CAN controller, CAN transceiver, and also a controller of its own. Vector tool, may I know what does it require for, Ajit? It's used for the CAN communication. See, it completely depends on what CAN, like what CAN controller you have selected. So there will be certain configurations to be made. So whatever tool you have to use for the development of the board, or whatever tool you have to use for the programming, it completely varies from controller to controller. Okay, fine. Now let us continue with the CAN. As I was saying, every device in the network, we refer it as nodes. So each node should have controller, CAN controller, and CAN transceiver. So CAN transceiver is one side having analog, the other side it is digital. Okay. Now proceeding ahead, let me go back to the previous slide. Okay. So first we saw was the example of the devices in the network. Internal ADC for the transceiver. So again, that depends. Okay, actually transceiver is the one which converts analog to a digital value. So yes, it should have ADC inside it for sure. Now if it has ADC inside it, so that's well and good. So because it's the task of the transceiver to do it, and if there is no, you may have to connect it externally. It, as I said, it completely depends on the hardware you're buying. So it varies from one to another. The features are going to vary. Okay, fine. So let me go back. Now we are done with the examples and we have to look at the versions of the can. So coming to the versions of the can, there are so many versions. The very first column represents the nomenclature. Nomenclature. The second one represents the standardization number being given by the ISO. Then we have maximum signaling rate and the length of the identifier. So it's the speed and the length of the identifier. Now, what is an identifier? We will see it a bit late. Let us now concentrate on this versions only. So we have a low speed can of 11 bits identifier. So this is the ISO standardization, and the speed at which the communication happens is 125 kilobits per second. So that is low speed can. There is CAN 2.0A with this standardization. So this has a 11 bits identifier with a speed of 1 megabits per second. CAN 2.0B has again a maximum signaling rate of 1 megabits per second and the identifier is of 29 bits. Okay, so these are the versions of the CAN communication protocol. Now again, can you show the previous slide once? Okay, so here is the previous slide. Okay. Now what happens is, usually in this case, we first have to understand how exactly is the communication happening. Now assume, just like the I2C communication protocol, so there are multiple devices in the network, and each device in the network, we call it as nodes when it comes to the CAN communication protocol. Now, just like I2C, in this case also, first of all, this is an asynchronous communication and protocol, and there is a triggering mechanism definitely required. So even though I2C was a synchronous protocol, it still used the help of start and stop bits to seek the attention of the receiver. Now, especially because it's an asynchronous protocol, the need of start and stop bits are really required. So when the communication should be established, as usual, the very first bit it gets transmitted is always a start bit. Now, in fact, even before you transmit the start bit, you have to remember to check whether the bus has been idle or not, correct? I have to first check if the bus has been idle or not, then I'm going to transmit the start bit. There's a doubt. We are configuring protocol through software, how it affects the speed for different versions. So that depends on the CAN controller you have bought. So some CAN controllers will be working with one speed. So some CAN CAN controllers will be working with another speed. So you will get different controllers, CAN controllers with different speeds. So you are supposed to choose according to the requirement. So we are not going to use any CAN version because, as I said, the programming is available only for UART and SPI. So we don't have support for CAN to be established. Okay. So as I said, we are trying to establish the communication between two nodes. Please understand this is very important. We may not have programming part, but you should at least be knowing how the CAN controller is working or how the CAN communication protocol is taking its steps one after the other to establish the communication. Now assume I have multiple nodes in the network, and just like I2C communication protocol, here also I have to transmit the start bit. Now before I transmit the start bit, I have to make sure if the bus has been idle or not. Now the moment whoever is the transmitter identifies the bus has been idle, directly message gets transmitted in the network. Now in the network, assume there are n number of nodes, and one of the device is trying to transmit some data. So can you tell me who is going to receive that data? So who is going to receive the data in the network? Every device in the network is going to receive the data in the network. So what it does is, first it is going to check if there is a bus being idle or not. And once the bus is being idle, so it is going to start transmitting the data. And everybody in the network is going to receive that particular data. Now, when the data is being transmitted, every data will have an identifier associated to it. Okay. So identifier associated to it. Whatever message I'm going to transmit will have an identifier associated to it. Because everybody is receiving the data. Don't you think I have to establish the communication with respect to one particular node? So I may have to communicate with one particular node or sometimes more also. I'll come with an example. So every message I'm going to transmit here is going to have its own identifier. Now, to make you understand what exactly is an identifier, let me go with some non-technical examples. Okay. Now, assume we are in a class. Okay. So, as of now, we are in a class. I have got 50 participants in my class, and I'm going to transmit a message. And assume the message is all boys start working on assignment number 30. Okay, that's the message I'm going to transmit. I say all boys start working on assignment number 30. Now, when I come to the class and make this announcement, who and all will be able to hear that announcement I made? Everybody in the class will be hearing it. But who do you think should take the response of it? Do you think everybody in the class will start working on assignment number 30? Do you think everybody in the class will work? What did I say as a message? So I said all boys in the class start working on assignment number 30. So I have an identifier there called boys, and all boys in the class are going to start working on assignment number 30. Correct? Now boys is the identifier here. Now boys means, can you understand that I'm speaking about more than one person at a time? Can you correlate? I'm speaking about more than one person at a time. So remember that can happen in the CAN communication protocol also. So in the CAN communication protocol, if one device is trying to transmit some data, multiple devices in the network may have to take action accordingly. So we also call CAN as a broadcasting communication protocol also. So it is capable of broadcasting the data as well. Okay. So in my message, when I said all boys start working on assignment number 30, all boys will have to start working on assignment number 30. Okay. Same as that. So in our network also, we will have multiple nodes, and whichever nodes matches with the message, so they are going to start working on the message. So this protocol is a multicast protocol or broadcast. Broadcast in the sense that would be wrong because everyone should have to receive it. I would say multicast. Okay. So this communication protocol is a multicast protocol, and there are possibilities that multiple nodes are going to accept the message and they will start working on that particular message. Okay. Now, as per our discussion, what type of protocol is CAN communication protocol? So it's multi-master, multi-slave. Okay. But apart from that, it's a multi-master, multi-slave communication protocol. Apart from that, what else? It's an asynchronous protocol, and what is the direction? So of the data line. So what you can do? Yes, it's a half duplex communication protocol. Now half duplex means how many data lines do I need? How many data lines do I need to achieve half duplexity? Only one bidirectional data line, right? Is there a need of a clock line here? Do I have to take a clock line? No. Then why do you think there are two lines here in the network? Can you see there are two lines here in the network? So one in black color, the other one in green color. Can you observe that? Okay. Okay. So I was telling that when it comes to the CAN communication protocol, it's an asynchronous protocol with only one bidirectional data line. But what you see here is that we have two lines here. Okay. And in fact, when it comes to the CAN communication protocol, so it's an analog protocol. That means whenever you have to transmit the data or receive the data, it happens in an analog way, and that is with the help of two twisted pair cables. So there is a twisted pair cable as you can observe here. Okay. So we have two cables here. It is in the form of a twisted cable. So we call it as a twisted pair cable. Okay. In I2C, can't we achieve multicast? No, Shreya. So we cannot achieve multicast in I2C. That is not possible. So it's a multi-master, multi-slave, but communication happens between one master and one slave at a time. But here, it's a multi-master, multi-slave, also multicasting, means one can communicate with multiple devices at a time. Okay. And as you can see, the communication happens with the help of a single data line. It is in fact a single data line. It is a twisted pair cable. Okay. And we are going to make use of the twisted pair cable for the data transmission. Now, what is the advantage of a twisted pair cable? So I wanted a single data line. I could have gone with the single digital data line. But why am I choosing a twisted pair cable? Or why CAN is making use of a twisted pair cable? Now, the biggest advantage of having a twisted pair cable is it allows noise cancellation. So less noise is going to get reflected. Every transmission will have a termination at the end. So just like other transmission, CAN also will have a terminated register around 120 ohms. And this CAN is working with the principle of NRZ. So have you heard of NRZ? Have you ever heard of NRZ? So NRZ stands for non-return to zero. Okay. So we have NRZ which represents non-return to zero. Now, so as I said, the twisted pair cables are going to work with the concept of non-return to zero. So if you take this twisted pair cable, I have two cables here. So one is called as CAN high, the other one is called as CAN low. Okay, so let me name it. So one is let's say CAN high, the other one is CAN low. Okay, so whenever I have to transmit the data, I'm going to make use of two lines. So now assume I want to transmit the data. So we have to understand how the data transmission happens with the help of CAN high and CAN low. So here observe the CAN transceiver is analog at one side, digital on the other side. So whenever I have to transmit the data, okay, so assume the controller has to transmit some data. So controller is going to give a digital value. So to that digital value will be converted to an analog value, and analog value gets transmitted by the CAN transceiver. Similarly, if I'm receiving some data, CAN transceiver receives an analog value, it converts it into a digital value and gives it to the user. So digital value means this is again, please understand, a serial communication protocol. Data transmission happens bit by bit. So now, how is the analog communication happening for a digital value? Please understand, as I said, we are going to make use of CAN high and CAN low, the two wires of the twisted pair cable. Now, how does a 0 gets transmitted and how does a 1 gets transmitted? So, I'm going to take the representation here. So, on one side, I'm going to have, let's say, voltage represented. Okay. So now I would say this is 0 volts. This is 5 volts. This is 2.5 volts. This is 3.5 volts. This is 1.5 volts. Okay. So let me write it down here. This is 5 volts. Okay. This is 3.5 volts. This is 2.5 volts. This is 1.5 volts. And this is 0 volts. 0 volts. Okay. Now, assume the data I have got to transmit is 1010. Okay. So, I want to transmit a data 1010. So, whenever I have to transmit a 1, a bias voltage gets transmitted on both CAN high and CAN low. Bias voltage means the middle voltage. So when I have to transmit a 1, both CAN high and CAN low are going to transmit a bias voltage, that is 2.5 volts in this example. So I wanted to transmit a 1 here. So let's say I want to transmit a 1. Okay. So both CAN high and CAN low, let me write it here. Both CAN high and CAN low are going to transmit the bias voltage, that is 2.5 volts. Now assume I want to transmit a 0. So if I have to transmit a 0, CAN high should carry 3.5 volts and CAN low should carry 1.5 volts. Okay. So whenever I have to transmit a 0, CAN high should carry 3.5 volts and CAN low should carry 1.5 volts. Okay, let me say it here. CAN high, this is CAN low. Okay, please understand, when it comes to the CAN communication protocol, so I want to transmit the data, assume 1010. So in case of CAN communication protocol, for the sake of data transmission or reception, so we are going to make use of a twisted pair cable which works with respect to the analog signals. Okay. The reason for having a twisted pair cable for the data transmission or reception is it reduces the noise being absorbed. So it has a good capacity of noise cancellation. Now, whenever I want to transmit a 1, okay, so both CAN high and CAN low will carry 2.5 volts with them. So when CAN transceiver identifies 2.5 volts on both CAN high and CAN low, the CAN transceiver says the controller that there is a 2.5 volts in both the lines. There is a 1 being identified. Okay. So whenever CAN transceiver sees a 1, means whenever CAN transceiver sees 2.5 volts on CAN high and CAN low, it decides that there is a 1 being transmitted. Now similarly, if you have to transmit a 1, CAN transceiver transmits 2.5 volts on both the can high and can low line. Okay. Similarly, when I have to transmit a 0, can high should carry 3.5 volts of power supply and can low should carry 1.5 volts of power supply. Okay. How to reduce the noise? It is built in. So the lines, okay, they are going to be sensitive. So they are not going to absorb noise. Okay. So there is noise cancellation. There will be a mechanism to cancel the noise. Yes, on-chip filtering. It is same as on-chip filtering. So that is for digital, in fact, and here it is for an analog line. Okay, Abdul is asking data bits in I2C, UART, SPI all transmits digital bits through wires only, right? But in CAN through data bits transmitted in twisted pair cable and in analog form, not digital like above protocols. Correct. Yes, Abdul, that is right. Okay, to transmit one, CAN high and CAN low should carry 2.5 volts. To transmit a 0, CAN high should carry 3.5 volts and CAN low should carry 1.5 volts. Now again I want to transmit a 1. So what should CAN high and CAN low carry? If I have to transmit a 1, yes, both of them should carry 2.5 volts. That is to transmit a 1 like this. Now again, I want to transmit a 0. So what should CAN high carry to transmit a 0? So CAN high should carry 3.5 volts and CAN low should carry 1.5 volts. So like this, you can do the data transmission on an analog twisted pair cable whenever you have to transmit the bits with the help of CAN communication protocol. Understood? Okay. So like this, not just in the transmission, even in the reception. So when data is being received, if CAN transceiver sees 3.5 volts on CAN high and 1.5 volts on CAN low, it will understand that there will be a 0 received. And if it sees 2.5 volts in both the lines, it is understood that there is a 1 received. So while the transmission also happens, the transmission happens the same way. Okay. So non-return to 0 is similar to that. So you will not transmit the 0 as it is or 1 as it is. So you are going to have a analog voltage for each of the value you want to transmit, and accordingly transmission and reception are going to happen. Okay. Understood how data gets transmitted with the help of twisted pair cable? Okay. So like this, the same way transmission happens from the physical side. So after examples and versions, as I said, okay. So here, coming back to the basic concepts. So I have examples, we saw the versions. The next thing is, there is an absence of node addressing. So you don't have an address provided to the each node. So as that of your I2C communication protocol, in I2C, every device in the network has its own unique address given to it. But here, you don't have an address. In fact, you have something called as an identifier. Okay. And this identifier can be common to multiple devices in the network. Okay. That is why we can achieve multicasting. So multiple devices in the network can have the same identifier. That is possible. So whoever's identifier is going to get matched, so that particular device is going to receive the data and take the action accordingly. So in I2C, it was a software addressable communication protocol which was transmitting a unique address. So here addressing is absent. So whatever message you are going to transmit is having something called as the identifier. Now, based on the identifier, the message gets accepted, and this one is a multi-master, multi-slave protocol. Okay. Now, what happens if multiple masters start communicating at the same time? So as I said, there are no masters I can call. I would say, what happens if two nodes start communicating at the same time? How many can transmit the data at a time? How many devices? Only one device can transmit the data at a time. Okay. So only one device is going to transmit the data at a time. So here I'm going to have multiple devices starting the communication at the same time. So again, there can be only one bus who's there can be only one device who's going to win the bus, and that is with the help of CSMA. So collision detection is actually done with the help of CSMA. So it's a non-destructive arbitration mode. Okay. So it is given by the CSMA with collision detection. Okay. Arbitration system here is by the carrier sense multiple access protocol. So CSMA is carrier sense multiple access protocol. And this is separate, and simple transmission medium is available. As I said, there is a twisted pair cable with CAN high and CAN low. Are you hearing any disturbance from my side? Is there any disturbance, some noise? Okay, please wait. Can you please confirm if the sound is still loud? Is it still loud? Okay. So I'm trying as much as possible. There's some occasion going on because of the festival throughout the week here and near my place. So maybe that is the noise. Okay. So let us continue with the next thing. So after that, let us look at the properties of the I2C communication protocol. So sorry, the CAN communication protocol. So first and the foremost thing is, so you have a layered architecture here. Okay. So CAN is actually going to work with the layered architecture. So I'm going to get back to the layered architecture. First, let us look at the properties. The very first property is prioritization of the messages. So here, whichever message is going to have the lowest identifier is going to win the bus. So previously in the I2C communication protocol, we had something called as data arbitration. So whichever had the lowest message, whichever master had the lowest message was going to win the bus. But here, whichever message has the lowest data, so I would say whichever identifier is lowest, so that is going to win the bus. That node is going to win the bus. So that is the first feature. And especially when it comes to the multi-master communication, that is when two masters are communicating at the same time, or two nodes are communicating at the same time, only one can continue to communicate in that line. So who gets the priority is the one which has the lowest identifier. So that is going to have the highest priority. Then there is a guarantee of latency time also. So when it comes to the CAN communication protocol, there is a guarantee to the latency time. That means the time taken to transmit the data, low ID means, so we will see what exactly a ID is, how exactly the ID looks like going ahead. You can see lower ID means, for example, let's say very similar to that of data arbitration. If one has 1010 as the ID, the other has 0000 as the ID, the one with 0000 is going to win the bus. Or some of the identifiers are of 11 bits, some of the identifiers are of 21 bits. So 11 bits identifier are going to win the bus in that case. Okay. All right. So I was speaking about guarantee of latency time. So there is a guarantee of the latency time. That means the time taken to transmit from one point to another point is always guaranteed. Okay. It is having the same data rate. Doesn't matter how far the nodes are situated. All of these are being tested and proven, and it is always the same. So that fixed latency means the time taken for the data to reach from one node to another node always remains the same. So whichever nodes you take, so how far the nodes are doesn't matter. So it is going to make sure that the data is received by the particular node on a given time. Okay. Next, it is having configuration flexibility. Okay. So that means anytime I can add a new node, anytime I can remove an existing node which is already available. Okay. So we have that flexibility. Next one is it's a multicast reception with time synchronization. So yes, as I already said, so it's a multicast communication protocol. If you're transmitting a data, there are chances that multiple devices in the network are going to accept it. And with the time synchronization means every device, for example, if 5 of them are receiving the data, all 5 of them will receive at the same time. So it's a multicast reception with time synchronization. Okay. Then there is a system-wide data consistency. So you cannot suspect the quality of the data being transmitted. So if one node is receiving one data, if the other node is also receiving the same data, I can guarantee that the data is always consistent between the two devices. Okay, so generally getting errors with the help of CAN protocol is a very less scenario, I would say very rare scenario. So generally data consistency is always maintained irrespective of the nodes. Okay, so you cannot suspect the quality here. An error is in fact an error. Error gets identified, but it is, as I said, a very less chance of getting an error identified. Then I have multi-master, means multiple nodes can start communicating at the same time. So there can be multiple nodes who wants to start the communication at the same time, but only one is going to win the bus. Then we have error detection and error signaling. So some of the error gets identified, some of the error gets signaled also. So only identifying is not sufficient. For the user to correct that error, it has to be signaled. Very few of the errors will be signaled, but some of the errors are only detected. Then we have automatic retransmission. Like RAC and repeat start. Are you talking about automatic retransmission, Abdul? Okay. So no. When it comes to the RACN and I2C, it's repeat start. That is, once you are done communicating, if you want to continue to communicate with the same device, you have to do repeat start. But here what automatic retransmission means is, now in case of I2C communication protocol, when two masters start communicating at the same time, only one master is going to continue the communication. One has to back out, right? So the one who backed out has to again come back, check if the network is free, and he has to again initiate his transmission. So that happens in case of I2C. But in case of CAN communication protocol, when data transmission happens between two nodes, if two nodes start communicating at the same time, only one node will win the bus, the other node is going to back out. Now, once the data communication is done between the nodes, whichever node backed out, so that node's data will be automatically retransmitted once the bus gets idle. Okay, so once the bus gets idle, whichever node backed out previously, that node's data will be transmitted by default. So you don't have to make that node come again and check the bus idle and all. So automatically, once the bus gets idle, the retransmission of the data is going to happen. No, so in I2C, we don't have automatic retransmission. That is not available in I2C. Next one is we have a distinction made between temporary errors and permanent failures of nodes and autonomous switching off of defect nodes. So we have a distinction made. We can identify which one is a temporary error, which one is a permanent error. And according to that, you are going to identify the failures of the nodes as well. Now, if any node is found to be defective, it is causing the problem in the network for multiple times. So the CAN communication protocol automatically switches off that particular node and removes it from the particular network. So that is the CAN communication protocol. Understood the properties? Okay. So the next we have got is, as I said, the CAN is going to work on a layered architecture. Now, have you heard of OSI model? The basic theoretical model. Have you heard of OSI model? How many layers does it have? Yes, it has 7 layers. These are the 7 layers of the OSI module. So application layer, presentation layer, session layer, transportation layer, network layer, data link layer, and the physical layer. Now, our CAN protocol is also derived from the same OSI model, but we don't have 7 different layers like this. In fact, we have only 3 layers. The only 3 important layers are available in the CAN. So we have application layer, we have data link layer, we have physical layer. Now let us understand what happens in each layer. So application layer is your controller. So your microcontroller is the application layer. Your data link layer is the CAN controller. Physical layer is the CAN transceiver. So as you know, in the CAN, every node should have 3 important things. So one is a normal controller, the other one is CAN controller, then the third one is CAN transceiver. So CAN is made up of only 3 layers: application layer, data link layer, and physical layer. Application layer represents the controller, data link layer represents the CAN controller, physical layer represents the CAN transceiver. So we are seeing what happens in each layer. The very first one is the data link layer. Now in data link layer, there are certain things happening. The first one is LLC, which is also called as logical link control. So it has the acceptance of filtering, means whoever is going to accept the message, they have the acceptance of filtering. Okay. Then we have overload notification. So if your data is overloaded, you can get, if you're not getting enough time to accept the data, then it has overload notification also. There is recovery management. If you are going out of the bus, then this layer does the recovery management. Then we have MAC, which stands for medium access control. So here data encryption, data decryption, I would say data encapsulation, data decapsulation is going to happen. The frame coding is going to happen. We have something called as stuffing and destuffing rule. We will discuss it later. So that is followed by the CAN communication protocol. Then this layer also detects the error. So if there is any signaling to be done to the error, so that is also done in the data link layer. So if any acknowledgement has to be sent, that is sent by the data link layer. And if you have to do any serialization or deserialization of the message, that is also done with the same layer. These are the duties of the data link layer. And coming to the physical layer, we have bit encoding, bit decoding, the timing, and synchronization, which happens at the physical layer. So as I said, application layer is your controller, data link layer is your CAN controller, physical layer is your CAN transceiver. Serialization or deserialization, yes. So if you have to transmit the data, like let's say multiple bits of data, you want to transmit it bit by bit, so you have to do the serialization of the data. Deserialization means once you collect the data serially one after the other, you have to frame one particular data. So that is deserialization, which happens at the data link layer. Okay. So LLC tasks are done by the application layer. No, LLC tasks are also done by the data link layer. So application layer will have your controller only, which controls all other peripherals of your network. I mean, of your board, or the things which have been connected to the controller. Okay, fine. So the next one we have got is the most important. So we have something called as the frame format. So we will move to the frame format. Please take a break of 2 minutes. We will continue. Okay, so let us proceed with the next. So I would say this is like the most important feature of the CAN, or this is the most important thing we have to be discussing in the CAN communication protocol. So what we are going to send at the end is a frame. So we have to understand the frame format when it comes to the CAN communication protocol. And this is one of the most interesting things when it comes to the CAN protocol. So as I said at the end, I'm going to have a frame transmitter. So let us understand the different frames and the frame formats. Now there are two formats of frame. One we call it as a standard frame. The other one we call it as an extended frame. Okay. Now how are you going to decide whether it's a standard frame or an extended frame? I2C didn't have a frame format, right? No, I2C specifically didn't have a particular format to be carried. Okay, but we have it in the CAN. So when in case of CAN protocol, if we have to transmit the data, I either will transmit a standard frame or I'm going to transmit an extended frame. Now what makes the difference between the standard frame and the extended frame? So when it is standard frame, so you are going to identify with respect to the number of bits in the identifier. Now, if the identifier of the frame has 11 bits, it represents a standard frame. And if the identifier of the frame has 29 bits, we call it as an extended frame. Okay. So if the identifier is of 11 bits, it's an standard frame. If the identifier is of 29 bits, it's an extended frame. Now, what are the different types of the frames we are going to transmit? So we have data frame, we have remote frame, error frame, and overload frame. Okay. Now, if you have to know when are we going to make use of these frames, first one is the data frame, which is used to have the data transmitted. So if you have some data to be transmitted from one node to another, you're going to transmit a data frame. Now, if you want to ask for a data from another device, you are going to request for the data with the help of a remote frame. So assume I want some data, I'm going to ask you, please give me the data. So I'm going to make a request by transmitting a remote frame. Okay, that is remote frame. So data frame is I'm going to transmit some data with the help of data frame. I'm going to request for some data with the help of remote frame. Now, if there is any error happening while the data transmission or reception is happening, there will be an error frame transmitted. And if you want to leave some timestamp, you want to give some delay between the two data frames or between the two remote frames or between a data and a remote frame, you're going to transmit a overload frame. Okay, so these are the four types of the frames. We have data frame, remote frame, error frame, overload frame. So data frame will be transmitted if you have a data to be transmitted. If you want to request for some data, you transmit a remote frame. If there is any error occurring between the data transmission, there will be an error frame transmitted. And if there is some time gap to be given between the two, so we are going to have a overload frame transmitted. So these are the frame types we are going to transmit whenever we have the communication to be established between the two devices. And each of the frame are made up of certain frame fields. So let us first discuss the frame fields, then discuss the frame types. Okay. Now, first of all, as I said, whenever I have to transmit a data, I'm going to transmit a data frame. Now, what and all fields does a data frame consist of? So first we are going to speak about the data frame. Now coming to the data frame, so let me talk about CAN protocol. So I'm going to transmit a data frame. So data frame gets transmitted whenever I have a data to be transmitted. Okay, so data to be transmitted. Now this data frame is made up of 7 different fields. Okay, so data frame is made of 7 fields. Now, which are those 7 fields? Let me write it one after the other. The very first field you have got in the data frame is a start of the frame field. Okay, so I would say the very first field as start of the frame field. Okay, so that's the very first field. After the start of the frame field, we are going to have an arbitration field. Okay, arbitration field. Okay, arbitration field. So first start of the frame field. So in fact, start of the frame fields are of 7 bits. Okay, so that is to represent the start of a particular frame. Then we have arbitration field. So here in case of arbitration field, so this is the field which is going to get decided as who is going to win the bus. So looking at the arbitration field, we can decide who is going to win the bus. Then after the arbitration field, we have control field. Okay, there's control field. I'll remove this field. So start of the frame field, arbitration field, control field. Then you have the data field itself. Then you have, let's say, CRC check field. Then you have acknowledgement field. I would say ACK. So this is acknowledgement field and end of the frame field. Okay. So EOF is end of the frame field. So please understand the data frame is made up of 7 different fields. So first is start of the frame field. Then we have arbitration field. So this arbitration field is either of 12 bits or it is of 32 bits. Okay. So start of the frame field is of 7 bits. Arbitration field is of 12 or 32 bits. Then we have control field which is made up of 6 bits. Then we have data field which is made up of 0 to 8 bytes. Okay, I would say 0 to 64 bits. So it can be anywhere between 0 to 64 bits. Then we have a CRC check which is of 16 bits again. Okay, this is of 16 bits. Then we have end of the frame field which is of 7 bits. Sorry, acknowledgement I missed. So this is 7 bits. Okay, and I think acknowledgement has, let me check once. So I think 2 bits. Okay, acknowledgement is of 2 bits. Okay, so any data frame you take, so that will be transmitted if you have a data to be sent. So it is made up of 7 fields. Start of the frame field, arbitration field, control field, data field, CRC field, acknowledgement field, and end of the frame field. Start of the frame field has 7 bits, arbitration field has 12 or 32 bits, control field has 6 bits, data field has 0 to 64 bits, cyclic redundancy check CRC field has 16 bits, acknowledgement has 2 bits, and end of the frame has 7 bits. Now let us understand each of the field. The first one is start of the frame field. Now start of the frame field. Oh, so start of the frame, sorry, it is not 7 bits, it's just a single bit. Yeah. So start of the frame field is a single bit and it is always a low bit. Now what do you mean by a low bit? So start of the frame field is always a low bit. What do you mean by low bit? Low bit or high bit? You should be aware of it. No. So low bit is a 0, high bit is 1. Okay. So when I say 0 or 1, transmission happens according to the twisted pair cable. Now let us speak things with respect to zeros and ones only. So when you say zeros and ones, accordingly the transmission is going to happen. So start of the frame is a single bit, it is a low bit, so we call it as 0. So 0 here is called as a dominating bit, 1 we call it as recessive bit. So we have a name given, 0 is called as a dominating bit and 1 is called as a recessive bit. Now the very first thing is start of the frame field. The very first bit which gets transmitted in the data frame is start of the frame field. So when start of the frame is being transmitted, so everybody in the device, in the network are going to pay the attention. Now after the start of the frame field, which is just a 0, I have to expect an arbitration field. When every device in the network receives a 0, they are going to pay attention, and now you are going to have a arbitration field transmitted. Now when it comes to the arbitration field, so I have 12 or 32 bits. Now arbitration field little bit depends on the control field. So let me first discuss the control field. So when it comes to the control field, it is made up of 6 different bits. The very first bit is let's say IDE or slash R1. Okay, reserve 1 bit. Then reserve 0 bit. Then we have data length count. Okay, DLC3. Then DLC2, DLC1 and DLC0. Okay, these are the 6 bits of the control field. So IDE slash R1 is the very first bit, R0 is the second bit, DLC3 to DLC0 are the next 4 bits. Now, so I will speak about R1 later. R0 is a reserved bit. Okay, so R0 is a reserved bit, and DLC3 to DLC0 represents the amount of data you have got to transmit. So whether there is 1 bit of data to, 1 byte of data to be transmitted, 0 bytes of data, 1 byte, 2 byte, 3 byte, 4 byte. So that is decided depending on the control field. If there is 0, 0, 1, 0. So can you tell me what will be the size of the data field? How many bytes of data am I going to transmit? Yes, I'm going to transmit 2 bytes of data. Okay. Similarly, if I write 0, 1, 0, 1, actually 0. So now how many bits? How many bytes? There will be 4 bytes of data being transmitted. The size of the data field varies accordingly. Okay. So control field, whatever it has, so accordingly the size of the data field is going to vary. Okay. So whatever data needs to be transmitted, we have to put it in the data field. Data field can vary from 0 to 64 bits. So that is 0 to 8 bytes, and that will be decided with the 4 bits available on the control field. Okay. Now R0 is a reserved bit. So it is reserved for some specific operations. Now what does this IDE slash R1 represents? So let me keep it a question mark as of now. We are going to discuss it later. Now coming to the arbitration field. Initially, as per the data frame, the node, whoever wants to start the communication, is going to transmit a start of the frame field. So in fact, before transmitting any frame, what should it make sure of? What should it make sure of before transmitting any frame? What should it make sure of? So don't you think it has to check for the bus idle condition? So first thing, yes, it has to check for a bus idle condition. And this one is an asynchronous communication protocol. Seeking the attention of the receiver is compulsory with the help of a triggering mechanism. So what the transmitter does is, it is first going to transmit the start of the frame field, which is always a 0. So all the nodes in the network are going to receive this start bit, and they understand that somebody is trying to do the communication. Let me pay some attention. Now all the nodes in the network are paying the attention, and after receiving the start of the frame field, now all the devices are expecting an arbitration field. Okay. Now this arbitration field is going to have 11 bits of identifier. Okay. So the arbitration field is going to have 11 bits of identifier. So there will be an identifier. Okay. So it is going to have 11 bits of identifier. Okay, wait. So don't decide it here itself. So in the arbitration, it can either be of 12 bits or 32 bits. So in the arbitration, first you get to see is 11 bits of identifier. Now, in case of I2C communication protocol, along with the unique address, what were you also passing? Yes, so you are also passing the intention, whether it is read or write intention. So here also, after you are done transmitting 11 bits of identifier, you have to transmit the intention also, whether it is read or write. So that is done with the help of RTR bit. Okay, so remote transmission request. So RTR stands for remote transmission remote transmission request. Okay, so 11 bits of identifier and 1 bit of intention, which is RTR. Now if RTR is 0, that represents the intention is right. Okay, and if RTR is 1, that represents the intention is read. Okay, so arbitration field is going to have 11 bits of identifier first and 1 bit of intention, that is RTR, stands for remote transmission request. 0 represents the write bit and 1 represents the read. Okay, so now as of this data frame, I'm going to transmit the data. What should be the RTR value? When I'm transmitting the data, what should be the RTR value? I'm going to write. So when it is write, I should have the value 0 here. In the data frame, I should have the value 0 here, which represents write. So 11 bits of identifier and 1 bit of RTR is received. Then what next? After arbitration, it is expecting the control field. The very first bit is ID/R1. Now what is this ID is? ID is nothing but identifier extension flag bit. Okay. So ID represents identifier extension flag bit. Now there are two types of frame format. One is a standard frame. The other one is an extended frame. Now what happens in a standard frame? How many bits of identifiers are available? So 11 bits of identifier, but with respect to the extended frame, what will be the length of the identifier? 29 bits. Now, when it comes to the IDE, it represents identifier extension flag bit. Now, whenever ID represents a value 0, okay, then it represents a standard frame. Okay, it represents a standard frame. Whenever ID is having the value 0, it represents a standard frame, and if it is representing the value 1, it represents an extended frame. Okay, now let us not go to the extended frame. Let us now concentrate on a standard frame. So when it comes to the data frame, okay, a standard data frame, I would say standard data frame, if you take, so first there is a start of the frame field. Okay, then I have 11 bits of identifier and 1 bit of extension, which corresponds to the arbitration field. Then I have ID representing what? So I would say 0, which represents start of the frame field. Then 11 plus 1 bits of identifier, sorry, 11 bits of identifier, identifier. Okay, so 11 bits of identifier and 1 bit of RTR. Then I have ID representing the value 0. So if ID is 0, it represents a standard frame. Then one reserved bit R1. Then 4 bits of the control flag, that is DLC3 to DLC0. Okay, then there will be data field, then there will be CRC field, then there will be acknowledgement field, then there will be end of the frame field. Okay, so this is the standard frame when it comes to the standard data frame. One start of the frame field, 11 bits of identifier, 1 bit of RTR. So I would say 0 here in fact, okay, because it is right. And 0 for ID representing the standard frame. R1 is reserved, DLC3 to DLC0, then data frame, data field, CRC field, acknowledgement field, end of the frame field. So in this case, if it is a standard data frame, I'm going to have how many bits of arbitration field? How many bits of arbitration field? So there is 12 bits of arbitration field. Now assume it's an extended data frame. Okay, extended data frame. Okay, now what will be the very first bit in the extended data frame? So what will be the very first bit in the extended data frame? It's the 0, which represents start of the frame field. Then after this, there will be 11 bits of identifier first. Okay, so 11 bits of identifier and 1 bit of RTR. So 0 represents right, so 1 bit of RTR. Then what should ID represent if it is a standard frame? Yes, so ID represents 1 if it is a standard frame. Sorry, it's a extended frame. So now ID is 1 representing an extended frame. How much should be the length of the identifier in that case? How much should be the length of the identifier? It has to be 29 bits. Okay, length of the identifier should be of 29 bits. So far, I have received 11 bits of identifiers. Now, when ID is seen as the value 1, the device understands that you are going to receive is a extended frame, out of which 11 bits of identifier are already received. How many else bits are left to be received out of 29 bits? There are 18 more bits to be received. So in that case, when IDE is returned with the value 1, it understands that whatever identifier it has received is not complete. So this RTR will get to be seen as substitute remote request. Okay, so this RTR will be seen by the node as substitute remote request. Okay, so it will be a substitute remote request. Now everyone understood that it is going to receive is an extended frame, so it is not an RTR, it's a substitute remote request, and that substitute remote request is always a 1. Okay, so it's a kind of substitute for the real remote request. It's a recessive bit. Now it is always going to be 1. And here in this protocol, as I said, 0 is called as a dominating bit and 1 is called as a recessive bit. Okay. So after this, 11 bits of identifier are received. So 1 SRR, 1 IDE, and how many more bits of identifier should I receive? How many more bits of identifier? So 18 more bits of extended identifier, I would say. Okay. Extended identifier. Okay, so now after this, I'm going to receive the control field. You can see One second. So now if you make a total of this, how much is it? How much is it if you make a total of it? Come on, 11 plus 1 plus 1 plus 18. So it's 31 bits. It's not 32, it's 31 bits. So 1 bit of RTR will be received right now. So 1 bit of RTR is a 0 in this case because I'm going for the purpose of writing. So it's a 0. Okay. So after this, I have to then expect a control bit. Okay. No, with start of the frame, it's not 32. So this much is the arbitration field. Okay. So I don't have a mechanism to highlight in different color. Okay, so I don't have a mechanism of identifying it in the different, representing it different colors. Let me just highlight here. Okay, so I would say these many, what I'm highlighting here is the arbitration field when it comes to the standard frame. So from here till here is the arbitration field of the extended data frame. Now after this you can expect a control field. So that is going to have R1. Okay. Then this is R0. Okay. So this is R1. Then R0 bit. Then you are going to expect DLC3 to DLC0. Then you are going to expect the data field. Then you are going to expect the CRC field. Then you are going to expect the end of the frame field. So this is extended data frame. So in standard data frame, one start of the frame field, 11 bits of identifier plus 0. So means 12 bits of arbitration field. Then this much what I'm highlighting is a part of control field. So the 6 bits. Then data field, CRC field, acknowledgement field, end of the frame field. In an extended frame, so 0 is the start of the frame field. Then you have 32 bits of identifier. Then R1, R0, DLC3 to DLC0 are the 6 bits of control field. Then data field, CRC field, acknowledgement field, and end of the frame field. Okay. If ID is equal to 1, then 18 bits of identifier gets extended. No. So if ID is 1, that means the identifier is of 29 bits. So you have to collect the next 18 bits as the extended identifier. Okay. So that is about the standard data frame and the extended data frame. R1 is ID. No. So ID is a part of arbitration field in case of extended data frame. So R1 is a reserved bit in case of control field. So ID is a part of control field if it is a standard frame, and ID is a part of arbitration field if it is an extended frame. So in that case, the very first bit of the control field will be reserve 1 bit. Why SOF not counting? So SOF is a separate field. So that's a separate field. Then you have arbitration field of 32 bits. Then you have control field of 6 bits. Then you have data frame of 0 to 64 bits. Then CRC field, ACK field, and end of the frame field. Understood this? Okay. So the data frame consists of 7 fields: the start of the frame field, arbitration field, control field, data field, CRC field, ACK field, and the end of the frame field. Okay. So if you see the control field, so control field, first bit is ID slash R1, R0, DLC3 to DLC0. The first bit is ID bit for the standard format, but it is a reserved 1 bit in the extended format. R0 is a reserved bit. DLC3 to DLC0 stands for the data length, and it can be anything from 0000 to 1000. Then arbitration field. So identifier of the standard format corresponds to the base ID of the extended format. So RTR bit stands for remote transmission request and must be 0 in a data frame, because 0 represents write, 1 represents read. So SRR bit is a substitute for the remote request and is a recessive bit, means it's a 1. The ID field indicates whether the identifier is extended and should be recessive in the extended format. So ID should be 1 to represent the frame format is the extended format. So the extended format also contains 18 bits of extended identifier. Understood the two fields? Okay. So next you have data field, which contains 0 to 8 bytes of data. It's a very simple field. If DLC3 to DLC0 has 100, means 8 representing in form of bits, but why taking 8 bytes? So the size of the data frame varies from 0 to 8 bytes only. Okay, so it is representing 8 value. Okay, it is not 8 bits, it is representing value 8. If DLC3 to DLC0 has 1000, it represents value 8. That means there will be 8 bytes of data to be transmitted. So that is the size of the data frame. That is data field. Then we have CRC field, which stands for cyclic redundancy check. It's a 16-bit field. So it has two separate sections. One we call it as CRC sequence, the other one is CRC delimiter. Now both CRC sequence and CRC delimiter are a part of CRC field. So CRC delimiter is always a recessive bit. So it is always a 1 here. Now CRC sequence is of 15 bits. Okay. CRC sequence is of 15 bits. Now what happens is, depending on the data, CRC delimiter is a single recessive bit. Recessive means 1. Okay. So what happens is, when it comes to the CRC field, once you are done transmitting any data, please understand, we have to check whether the data received is right or wrong. So how did you check it in case of UART protocol? So how did you identify whether the data you have transmitted is right or wrong? Yes, you had a parity bit. So here also I have to confirm if the data I have received is right or wrong. For that, there will be cyclic redundancy check sequence created, and that is generated with the help of a polynomial method. So basically there will be a polynomial method which is going to make use of the data it has collected, and accordingly it is going to generate a 15-bit sequence. Now if this 15-bit sequence generated by the receiver is a match to the 16-bit sequence being transmitted, then it is a confirmation that you have received the proper data. Else the data received is not proper. So what you do as a transmitter is, when you are transmitting the data, you also will transmit a CRC sequence which will have 15 bits of a sequence generated and 1 delimiter bit. Now receiver also generates the same CRC sequence depending on the data it has received. Now if the CRC sequence is a match, you can conclude that the data transmission is properly happening. If it is not correct, you can conclude that data transmission is not happening properly. Then after TRC field, we have an acknowledgement field, which is of 2 bits. Okay. And according to the acknowledgement bit, the first bit is acknowledgement bit, the other one is acknowledgement delimiter. So this bit will be set to 1 by the transmitter. It will be done 0 by the receiver. Okay. So it will be set to 1 by the transmitter, but will be reset to 0 if a receiver acknowledges the data frame. So we have a acknowledgement bit, we have an acknowledgement delimiter bit, which is always a 1. Okay, so that is acknowledgement, and the last end of the frame field is made up of 7 bits, and all 7 are recessive bits, means 7 ones. Okay, so data frame is made up of these many fields. Start of the frame field is a 0. Arbitration field is either of 12 bits or 32 bits. Control field is always 6 bits. Data field is of 0 to 8 bytes. CRC field is of 16 bits. Acknowledgement field is of 2 bits. And end of the frame is of 7 bits. So comprising of all of this, a data frame will be formed and it will be transmitted. Understood the data frame? Okay. So the next we have is a remote frame, overload frame, and the error frame. They are very simple frames. If you understand data frame, the rest of the frames are very simple. So tomorrow I may hardly require a half an hour of the class to complete this. I don't think I even need half an hour. So it's like 20 minutes of the class and we will be done with the module. So if time permits, I will start with the project also. And so receiver also sends back the acknowledgement like I2C. Yes, sir. So to give the acknowledgement, it just pulls the line low. The acknowledgement bit will be made 0 by the receiver. Okay. Hope the class is all been clear. Please have your attendance mark before quitting. We will continue the rest of the next class. When will we have the module test? Somewhere in the next week. Okay. So here is your QR. Okay. Please have your attendance mark before quitting the session. Yeah, maybe after Dasra you will have your exam. So thanks for attending today's class. We'll continue tomorrow. Thank you all.